Thanks. Hi, my name is Mark Quinlan. I'm a field engineer at Neo4j, and presentation is on entity resolution and deduplication, some of the best practices from our field engineers. So I've been with Neo for about 7 years, and I'm a consulting engineer since the 1990s. So I've seen quite a few things, and this is a pretty common use case that we have. You can find me on LinkedIn and email me if you have any questions after this. Appreciate it. Okay, this is a really busy use case for us. We have a lot of requests for this because it's part of almost every project you have. You need to know who the people that you're dealing with are, the companies, the businesses, the digital assets that you're dealing with. So anytime you're building an application, you're frequently having to do deduplication. There's a lot of different approaches to it. It's critical for like financial fraud, universal business ownership projects. Some of our customers actually use Neo4j as the basis of the service that they sell, which is identity disambiguation and identity resolution. But really what it comes down to is there's a different approach for almost every project, but there are some patterns. So you need a subject matter expert who can define what your similarity patterns are for your particular domain, and also to fully understand and always keep in mind what are the costs of a false positive and a false negative, because nothing's perfect, but some are good enough in a lot of situations. And the tools we're going to talk about today are the graph data science tools, GenAI, and Cypher, and as well as some custom rules that we're using for this. Okay. Most people start off with simple graph traversals. It's the easiest way to get started. You're basically using Neo Cypher language to see how many people have shared entities. There's a lot of things you can do with a pure Cypher approach. And for some use cases, this is enough, but typically it's not. Typically, you're going to need something with a little more oomph to it when you start getting into deduping for tens of millions or hundreds of millions of things. You start looking for things like graph data science algorithms, community detection, and all the similarity algorithms that can really help you out for that. So we'll look at some of the patterns that are available there. One of the new things that we are looking at using and is starting to work really well, and I'll show it to you, is using vector indexing. And so some of the approximate nearest neighbor similarity calculations that you can use with the vector index in order to do deduping. So we're going to look at that. But it's almost always this and this and this, because what you're trying to do is really hit that, I'm confident that your that this entity is this, and your confidence score goes up when you start adding these things. None of these are silver bullets, but they all do work really well and can get you into the game. So this is the data model that I'm going to be using, and I chose this mainly because it's pretty common. We use it as a starting point for discussions. This is what you know about a person, and start thinking about how to dedupe things, and start looking at some of the larger circles here. These are nodes that I'm going to be using today for the presentation. But you obviously we're centered on persons. Persons have names. Persons have surnames. Persons have addresses. And for our GenAI example, we're going to be using persons have resumes. But you see lots of other identifiers. They have a credit card. They have a social security number. They have an occupation. They've used an IP address. Everything that you know about this person should be tied in. And that's the beauty of a graph. This makes it so easy to just say, hey, I know who that person is, or I think I know who that person is, and they bought a house at this address, or they gave this credit card, or they've been using this IP address. So the things that you know about that person, always you're trying to come up with as much context as possible. So if you take nothing else away from this presentation, context is king. Everything deals with context. The graph algorithms work better if you have context. The vector searching works better if you have context. The Cypher queries most certainly work better if you have context. So the more of these dots that you have in here, the more nodes that you have that you can use, the better off you are. Otherwise, we've got some solutions for that too. But typically, if you have context, you're going to be doing really well. Okay, So what I'm going to be talking about is using canonicalization. And that's the idea that you've got this gold master record that you're trying to keep nice and clean. And there's different approaches, but this one works really well where you've got this master record and you withhold updating it or merging records into it until you know that this is going to help your solution. So this is like taking a preventive record approach. So like you keep your incomplete records or you keep your candidate records in something like BigQuery. So you don't put them into the database and just throw them in there and then try to clean them up later. Cleaning up is difficult to do. Splitting these records is really a difficult task after you've merged two IDs together. But again, you're trying to create as clean a records as possible. So you might flag something as I tentatively inserted this record. Maybe it's not good yet, or you can tag it to an existing record, a node with a relationship that says, possibly this, evaluate later on. And the other thing I want to get across is that all of these decisions that you're making about what record got updated, what record didn't have enough information, had too low of a score, it didn't meet the criteria for doing an insert. Save that information. Save the factors that you looked at along with the decision that you made, because you can use that in your training. So the fact that you didn't insert some records, that's still very useful exercise. Keep that information. Keep it. BigQuery is fine, or throw it into another graph that you can use for your training processes. But really what you're trying to do is to look at similarity to see how effective, when this happens and this happens and this happens, do I improve this? So again, for your training models, keep the things you do, even when you reject a potential match. All right. First off, we have activity-based ER, and this is the lowest form of entity resolution. Typically, you do this only when you have nothing else to go on. So these aren't people that are, a lot. You don't have their social security numbers. Chances are, what you probably have is a typical website was stitched together something like this, using first-party and third-party cookies. So this is a good example is, and I'll show you the slide in a second, is where they had billions of impressions. People were coming in and using their IP address. And really all we're doing is keeping track of this person used this IP address, this person used this website. So are they the same person? Well, maybe, maybe not. It depends on the use case. So if you have nothing else, and really, your context is limited, and the cost of a false match is low, use this. And then you can start adding to it and say, hey, by the way, that IP address and that website, when they went to that website, a website that you own, oh, they signed up for something. Okay, now I've got a credit card. Now I've got a social security number. So you're going to keep adding to that. So in the early stages, all you have to go on is this. But take a company like, a big consortium, maybe they own entertainment parks, they own cruise ships, they own TV stations, that kind of thing. And you start seeing where they start seeing different views of that person, and then you can kind of stitch together these digital IDs. This is nothing to do with a graph makes it easier, and the graph algorithms that are used for that make it easier as well. But it's only when you have really limited context and and the cost of the false matches is really low. So this is a good example of that. This is Meredith Corp. This is one of the few that I'm allowed to talk about. Everybody does this approach, but it's one of the few that's in there. So they're essentially using community detection algorithms from our graph data science library in order to find communities. And essentially what they're using is they can use these communities to sort of create blocks. And so it's a blocking factor where you can then concentrate on that subsector and say, okay, let's go look at those guys and see how similar they are within that particular block. So these are like heavy duty approaches using very, very powerful algorithms, but algorithms that don't give you a real high degree of confidence. There could be a million reasons why these things are linked together. But the blocking, what it allows you to do is to narrow down the focus for other further analysis. Okay, so this is part of the shared identifier process. It's similar. So you have you have their web address and you have their IP address. They've been doing this, but now you start seeing, oh, they've logged in. Oh, now I've got an email address. Maybe it's a bogus email. Maybe it's from 10-minute emails. Maybe it's something silly. Maybe it's a social security number that's shared by 45,000 other people. Maybe it's a phone number. Maybe it's a bogus phone number. So, but being able to do this approach and say, who else uses this thing here? This is a common approach. It's Cypher only. It uses Cypher just for matching, for looking for similar IDs. Um, Everybody starts with this. It's great, but I typically don't like this approach. What I like to see is I will use this once I'm narrowing it down. So I'll use something else like community detection or the vector index for narrowing down my subgroup. And now I want to do some all pairs comparisons. Now I'm going to go look at them. Tell me what they have in common. I'm going to start looking at this because it's simple to use. It's just Cypher. You can do text comparisons, date comparisons, and geospatial comparison. You can explain it, and it's deterministic. These are all really great things, but it yields low quality results, so you don't rely on it all by itself. And it's only really good for exact matches only. They have this exact match on a social security number or something, or a name. Well, the world isn't always exact, and we'll get to that in a second. So it has a limitation there of exact matches only. And the relationships have to be in Neo. This doesn't really work that well if you're doing, say, pulling in records from Kafka. Like you're looking at a Kafka stream and you see this record here. Hey, what should I do with this? Should I insert it or not? Well, it's not in Neo, so you don't have any relationships to compare yet. So it's not a good candidate for that. It's more of a, okay, I'm cleaning some stuff up and I'm doing some analysis and say, okay, show me who this is, or it might be doing some fraud detection. Where I'm looking for these similarities. So shared identifiers, great idea, low quality results, but still useful. Maybe good enough for your application, maybe not. But again, you have to weigh that based upon your own policies. So like this here, is this the same person? So I've got Bob, I've got Robert, and I've got Bobby. So for that, I want to look at name analytics. I'm going to be doing how similar are their names, and I'll use phonetics, I'll use soundex, I'll do some other things with that. I could use phone number analytics, like, is that a real area code? Is that a bogus number, like 8675309 from that stupid song a long time ago? It could be an email address that just a bogus email. There could be profanity in there. There's lots of ways of analyzing email addresses, trying to find out if something's real reasonable or not. And then addresses. There's a ton of utilities that are available for looking at addresses. So basically, if you're trying to do matching, well, I'm going to do a comparison, but I might not have an exact match for a lot of different reasons. So what do? Well, you start looking at the basics. The really simple ones are the most common. They're Cypher functions like edit distance, similarity, phonetic, and these are basically saying how close is that string to this other string. It has almost nothing to do with names. It's just string comparisons. Like I'm looking at Robert and Bob. I can see the Levenstein and similarity, dice, meta, phonetics, and the statistics tell me that this is not the same person, because the words are really very different. But that's because it has no context. There's no semantics involved here. These are just string comparisons. So you use those when they are simple to use. They're useful for basic text field comparisons, like email addresses. Any text fields you can use this to say, are they the same? They're computationally, they're very fast, which we like, especially when you're doing millions of them. They're explainable and they're deterministic, which is also really good. Biggest problem is they have no semantic meaning. Like the difference in edits from the word friend to fiend is one letter. So the difference between friend and fiend, you swap out one letter and you go from one to the other. Well, so an edit distance of one is really good, but semantically, friend and fiend are really very different things. It's like loser and lover. Yeah, one letter all needs to be changed. That's it. But they're semantically very, very different. So think about that. Names are not just simple text fields. there's context to them, there's semantics to them. So there's a lot that goes on, and so and when because you don't get an exact match on Robert and Bob, well, you're going to get a lot of false negatives. You're going to get a ton of false negatives, but you might also get a lot of false positives because they did match on John or something with a lot of popularity. So we started with this idea of using something else, not just edit distance, but nicknames. So it's the idea that you can say, hey, I have this person here, Chris, and I have another person, Tina. Are they the same person? And so how similar are their names? Well, they fail in terms of the edit distances and all that kind of stuff. They don't sound alike, but you see that Chris has Chris has a nickname of Christina, um, and Christina has a nickname of Tina, and that's what was given. So I've got this common nickname in there. So I can go 2 hops out, and I can get a common nickname for this. And so I could use that information. Say maybe there's a 1 hop to get a name like Robert and Bob. That's 1 hop. If I go Chris to Christina to Christy to variations on that. Um, that's 2 hops, and I might not give a 2 hop score as high as I would. Uh, these are useful for first names. You can use them for surnames, not as much. That's when you get into common substitutions like McDonald, MacDonald with an A, and you get variations on that. So you might be able to say, like similar, but that's an approach that the genealogists will use, and we'll get to that in a minute. Okay. So again, it's not really useful for surnames. It will give you more false positives because now you're getting into well, maybe they did mean this, and so sometimes you go out a couple of hops and you get really weird. I never knew that was a nickname or something like that. And also it adds a lot of extra work because now you've got all these nodes and relationships that you're keeping track of in the database. And it also, and I forgot to list it here, but you do get fewer false negatives. Okay, and here's how it works. The code for doing that is really pretty simple, and I can see 1 hop away from Chris is Christine, Chris, Kristen, Christopher, and so on. 2 hops away is this other list, and I see the difference between Chris and Tina is 2 hops away. So I might be able to say, hey, yeah, that's worth a point, whereas an exact match is like 10 points, and then 1 hop away is 2 points. So you can do various scoring. So lots of fun. You can have regional variations on nicknames like Michael. Well, you might have Michael and Mike here in the U.S., but you might also have Michelle, variations on that. Tons of different spellings globally. So as we become a more global society, it makes it easier to say, well, they didn't match on Mike or Michael, but Michelle. And you kind of have to be careful with that because it's just a first name, all you're getting. And so if you're trying to do this where the names are common, you might end up with it's like, yeah, they match on some form of Michael, and that's not really a great idea to just put too much faith in that. So again, it becomes a scoring method that you're using, but it's not fantastic. Here's another way you can make that better, though. You can use term frequency and inverse document frequency. So this has been around forever, but basically the idea is that you're looking for things that are essentially uncommon. You're looking for uncommon names. Somebody that matches on an uncommon name should get more points in your scoring process than somebody with a really common name. So I see Smith is the most common name in my little database here. So they've got an inverse document frequency of 2 point something. Williams, Brown, Jones, and so on. But I look at these other names that are down there, Fairweather, Spade, and so on. There's only one person with those. So those are pretty rare names. And they're stupidly simple to calculate. It's trivial to calculate them. And you can also, they're based on your names, the names that are in your database. So it's not just some global table that you're using that's got names in it. But the stats, you calculate these once, you can use them and periodically refresh your stats based upon adding a bunch of data. But again, to go through your database, score everything, and then come up with the weights is really pretty good. But And then the other benefit from doing this is that the high cardinality values, they can be junk values. These could be just like, John Smith. I mean, really, John Smith. Um, Maybe the guy really, his name is John Smith, but you get a lot of junk values. And you have to think about also the idea of maybe adding one for your first names and for your last names, and then together. So you have like the name Vladimir, which is a fairly common name. Guerrero, which is a fairly common last name, depending on what part of the world you're on or part of the U.S. you're in. I'm in Northern California, and I hear that a lot. But Vladimir Guerrero is kind of an unusual name. Unless you're a baseball fan, then you know that there's some two really good players named Vladimir Guerrero. So again, you can use them individually and together. And so if you put them together as a full name and then do your IDF on that, that's worth some value. Okay. Also, for names, there are some really good organizations out there that deal a lot with names. And these are genealogical organizations like FamilySearch.com, Ancestry.com. The Mormon Church has unbelievable resources in this area. The U.S. Census, they want to help out. So they've got libraries and they've got a lot of different advice there. And then the International Genealogical Index is available. And so they have these substitution tables, transposed letters, guidance, some libraries that are available for being able to use nickname files. There's a lot of different tools that are out there. And these are more commonly for surnames, but they also have tools for first names only. And then they're also really good at identifying translated immigrant name variations. So my family's name was changed when they moved from Norway to the United States. Same with my wife, her family. So you can say, well, you didn't find it under this name here, but did you find it under this name here, which is somebody who decided to keep their name, or Johann versus John is going to be the translated or the immigrant names value. So anyway, it requires custom coding to put this stuff in, which is again can slow things down, but it's very deterministic. You can put these rules in, and you would want to do these when you're comparing two people. When you're looking at this, not when you're comparing a billion people to another billion people. That would be very, very, very slow process. So when you're doing this, it's very impractical for global all pairs comparisons. But also it can result in more false positives, because now you're giving, and that's not a bad thing, because what you're doing is you're giving this candidate name pair another chance to survive. You don't want a false negative by saying these are definitely not the same person. What you're hoping for is they're possibly the same person. And again, they warrant further attention, as opposed to no, they're not. Go ahead and insert this other record, and then you find out later on that they really are dupes. So a false positive is not a bad thing. Okay, addresses. What can we do with addresses? Addresses aren't simple strings. Just get that through your head right away. They're not simple strings. You can do string analysis, but there are so many different ways of doing addresses. At the Neo office, we just moved. We were at 111 East Fifth Avenue. So is that Fifth Avenue with an E? Is that did you leave in the avenue? Did you accidentally put street? Did you use the right zip code? Did you format it correctly? So these are all things that can be easily fixed by companies like Google. Will fix these for you. Also, when you're using addresses, it's a location. The address shouldn't be an attribute. It should be a thing. It should be an object, a node that's dedicated to that particular point on the planet. So it's a geospatial data type, but it should be a node, not a property with a link to it. Then it makes it very easy to see how often is that location being used, or who's nearby, that type of thing. So use properties for that, and always use a formatter. So I will typically run it through a formatter to get this nice standard format, which is on the next slide. I'll get this format, it's address, and I'll use that frequently as the key, or I'll do that as a comparison to see, how close were they text-wise. But again, there's semantics to the address. How close are together? And, we've had situations where somebody said, well, that can't be the same person because their addresses don't match. They're 5 feet apart, okay? Or somebody used apartment 1 and then somebody else used apartment 1A. Or Google will even tell you that that's 1A is not even a legitimate address. So that's available. And once you have them in geospatial data types, you get all of the goodies that go with it, like bounding box queries, being able to range searches and say, give me everything within 5 miles of this person here. So it's really useful for doing that. Validation address, validation APIs are really quite good. So when you're dealing with addresses, again, steal from the best. Those guys know what they're doing in terms of addresses. And another thing you can look at doing is using H3 libraries from Uber. And I really like this. It comes up with this capability. I'll get to the slide in a second, but it comes up with this ability to define something in different size hexagons. Some of the hexagons can be the size of countries, and they can be as small as city blocks. Being able to, where does this thing exist in space? Show me the things that are in the nearby hexagons. It makes it a lot easier to do. There's an address validation API from Google. So like I can see here that they fixed my zip code. They standardized the Ave versus Avenue. They spelled out Fifth Avenue as East Fifth Avenue because I neglected that. And they give me a nice full address to this. So if you're not using something like that, then, well, you should be. This is the H3 system from Uber. I really like this. Being able to very quickly identify what's where was somebody. GeoPoints are really handy, but sometimes this is also good enough to just say, hey, I'm in this particular hexagon, and from that hexagon I can see all of the 0 to 15 levels of granularity. So I can very easily see what's in the surrounding circle of hexagons. So it makes it pretty easy to do queries against that using various levels of granularity, depending on what kind of blocking factors you're looking for. Okay, all right, so people and addresses, we've got a lot of those. But we also have other things. We've got Neo has a lot of customers dealing with intellectual property. So these could be images, songs, movies, movie scripts, lots of different things. We're dealing with intellectual property, plus just the ability to distinguish with, if I've seen that photo before, is that one that we own? Now AI has generated something similar to it, but is that there? So being able to look at, do we already have a copy of this in our database? We might need to know, or it could be a long contract or PDF file, something like that. So digital assets are a little bit different. Almost all of them support metadata tags. So yeah, go ahead and use them. Put them in there and index those tags. And sometimes that's good enough. But what you also want to do is take this unstructured text and use the LLM embedding models. You convert them to standardized vectors, and now you can take those vectors of a song or document, which I'll do in a second. You take those vectors, you use those attributes, and you store those in Neo's new vector index. And now I can compare those and say, how similar is it to this? And so I can do similarity against unstructured things, which is fantastic. So being able to do that. So when you're doing that, you have to be concerned about the embedding models. It's quite easy to do in a POC. Trying to do this in production is a little more difficult because there's so much emphasis that's placed on the embedding process. And the embedding process is where every company is that's going to be their secret sauce as to how good their embedding processes are. And okay, again, we're going to be using Neo4j to store the embeddings, and you're going to use the vector query, which is really it's an approximate nearest neighbor search to find similar items. Then the nice thing about it is because you're storing it in the Neo indexes in the Neo database, you can then do post search filtering. We'll show that in a second, where you're going to be using a traversal to do additional processing. So ER deduping of digital assets, again, comes down to the quality of your embedding process. But once that's done, storing all the embeddings in Neo and doing similarity searches in Neo using the indexes, it's really pretty simple. Okay, using GenAI for deduping. So this is really new. And when I originally proposed this topic, I wasn't including this one. And since then, I've like, okay, I can see where I would really use this. And I've got one example um, where we'll go through in a second. But the idea is that Neo4j has right next to its native graph storage and its spatial and range indexes. It also has this new vector index. So I have this field over here called position. I know everything about this person, their certifications, what school they attended, where they got their degrees, their skills. But the job position is free-form text, and I want to know who has a similar job position. And for that, I need to know some semantics. I can do a name comparison and say, well, the words are similar, but I'm looking for Neo's ability, or the embedding process's ability to give semantics to that text. So you take that text and you embed it, which creates a vector, and the vector gets stored in Neo, and then you do a search. So let's see how that could possibly work. All right, as in my example, how many of you guys have seen this? This is less than a week old. And what they're doing is there's people out there, thousands and thousands of workers that are basically reusing IDs, they're reusing lots of different things in order to get jobs within companies. They then take the money from the companies and they're forwarding it back to North Korea. The FBI in St. Louis cracked this case, but it's like, how would I detect this if I were in HR, and now how would I look for the ones that are possibly in my company to do that, looking for that. So what I'm going to do is I'm going to look at the resumes that they're submitting. So people, for all of these things, they had to submit resumes, they had to go through interviews. So sometimes they would pay people to do interviews. But like a lot of things that are fraud, people are lazy. They think they're not going to get caught, so they're kind of lazy and reusing stuff. Like, okay, so how would we do that using the vector index? So what I'm looking for are similar resumes, and so I've got these persons over here in the blue. I've got these two persons. I've got Peggy Brown and Margaret Brown. And in case you didn't know, Peggy is actually a common nickname for Margaret, and that shows up in the nicknames file. But anyway, and I've got a different spelling. So I want to see how similar are these two people here. So basically, this person here submitted a resume. Now the resume has text on it, and the texts are in blocks like job one, job two, and they're usually in reverse chronological order. So you take those job blocks and we call them chunks. So you're going to split this thing into chunks. So every resume's got 2, 3, 4, 12 different chunks of text that are in there. The chunks are then sent to the embedding process, and they're using the semantics of OpenAI, or some of the other ones are looking at it, and they create embeddings for that. That goes into the Neo4j database. And then later on, this other person down here, she's got one also. So I want to compare them. Well, I can do a very easy comparison and say, hey, for this person here, for this resume, go find all of their chunks, and go find those people, and find me all of the resumes where there's similar chunks using some kind of scoring process. And the scoring process is then going to give me a resume that I can then see back to the person. So how does that work? Actually, it's stupidly simple to do. Here's the code for that. And you see over on the left, these are the results. So I have one person in there that I'm searching for, and they're looking at. Okay. Um, I see we're out of time here. For some reason, I thought I had 10 extra minutes. Uh, okay, my apologies for that. So thank you, Clark, for wrapping that up. Anyway, this is there's lots of different approaches to doing this, and um, look at the vector indexing process as one of them when you're trying to do similarity between existing ones, as well as um, using the graph data science approaches. The most common ones for that quickly are like community detection and similarity. So my apologies. I was originally informed I had 45 minutes, and apparently I don't. So that's on me. So thank you very much for your time. Uh, but if you have any questions, this will be posted. I will, in addition to the slides, I will have links to where the GitHub repos are, so you can see where that is, as well as the Bloom perspective. So when I'm looking at this person here, you can see, let's go look at the similar resumes for Thomas Stokes, and it's going to then calculate that based upon the jobs that this person has had. Why did it not come back? Okay, they're drawing. I'm in a bad network. So I found 496 resumes that are very similar to that. So this is that person there. And each of the documents, each of the green is a resume chunk. That's a job that they have in common. So based upon that, I can do this. So, okay. All right. My apologies. This take a look at the slides when they're out. You can go into a little more detail. And the Git repo, you can see this person here. Um, all of the green dots are similar chunks. Some people have 2 similar jobs. Some people have 7. Other people have, like down here, this person here not only has a bunch of similar resume chunks, but um, they also share a social security number. So it kind of gets into the ballpark of being able to find similar things. So okay. So questions? Do we have any questions? Looking for that. Okay, I don't have any questions. This is so again. I apologize. This is like really embarrassing. I've never done that before. Where I missed the time. So I appreciate that you sticking around. There's only one more session now between you and the end. Um, so similar resumes would be normal. Resumes are usually tailored for that position. Um, that's true. It kind of depends. How similar are they? So uh, if the similarity is really just astronomically high, like okay, if 2 job points, like if I list 2 points versus somebody's got 7, and somebody else matches on 3, what I want to do is I want to find out how similar they are. But really, what you're doing is you're taking this overall population of a million people, and you're trying to break it down into smaller chunks. Where I might want now, I'm only going to look very carefully at these 1,000 people. And so I can do, instead of doing an all pairs comparison of millions, I can do an all pairs comparison of thousands. And I can do those like in no time at all. So that's kind of what the point is. The ANN factoring, its biggest benefit, the only takeaway from this, its biggest benefit is you're using ANN to find similar things, similar enough to warrant further processing. So they become a blocking factor. So blocking is something that's normally used, uh, and ANN is a great way of doing that. So these are all blocking mechanisms. So blocking, yeah, like comparing every record, extremely expensive, like 500 billion comparisons. No, ANN as in, that's great. I'm sorry, I didn't explain my term. It's approximate nearest neighbors. So as opposed to true KNN. So like a true KNN is going to be a all pairs comparison with 500 billion comparisons. But I can do an ANN, which is going to get me in the ballpark very, very quickly. And so now I have a set of records. Now I can do an exhaustive, like Company X that I'm working with. They have a 93 step process in their rules engine for doing deduping. What they need is something that narrows it down. So now I can say you've got over 100 million of these things. Now, now I can limit it to the 1,000 you should pay attention to, and so that becomes the benefit of the vector, being able to do that. So I apologize for that. So no, great question. So again. my and I really do apologize for that. So my email address and LinkedIn are in here. Ask me questions. Send them to me, and I'd be more than happy to answer your questions or give you guidance on stuff. This is what we do, and I've got a ton of really smart friends. This is this is what our team looks like. We've got over 200 people that contributed to this presentation, and so yeah, ask us questions. This is what we love to do. So thanks for attending, and that's it.